Okay, so in part 2 of section 5.6, another theorem, the real numbers. So the next theorem basically tells us the number of real zeros a polynomial function has cannot have more. I'm sorry, let me try this again. The name of the theorem is the number of real zeros. What it tells us is that a polynomial function cannot have more real zeros than its degree. Kind of already knew this. We really did, because when we solved linear equations, we know we got one answer because they were x to the first power. When we solved quadratic equations, which were x squareds, we got two answers. So what if we have instead, this is example 3, back to that same polynomial function that we're eventually going to solve. F of x equals x cubed plus 8x squared plus 11x minus 20. How many zeros does this have? At most, we're going to have 3 real zeros, and that's because it's a degree 3. Because it's a degree 3 or a third degree polynomial equation. So at most it has 3 zeros. It will have 3 zeros eventually. Whether or not they are all real is another question. But for this section, all we're doing is finding those zeros. Okay, the next theorem is the rational zero theorem. And this one looks really ugly in the little box there, but it's really easy to apply it, which is what we're after. So if we have a polynomial function of degree 1 or higher, and there's the way we write out the polynomial function again, where each coefficient is an integer, very important, integer coefficients. If P over Q in lowest terms is a rational zero, then P must be a factor of A naught and Q must be a factor of A sub n. What the heck does that mean? So the issue is going to be, we know that if we use synthetic division and we get a 0 at the end, we found a factor. But how am I going to know what numbers to try in that synthetic division process? So the rational zero theorem gives us a list of numbers to try in the synthetic division process. So in example 4, it says, list the potential rational zeros of f of x is equal to 2x cubed plus 11x squared minus 7x minus 6. So for us, Q is always the first coefficient, P is always the last coefficient. So the possible rational zero. So this is just possible. It is also rational, and rational means that it has no radical. So this would be our terminating decimals, our repeating decimals, our fractions, and our integer values. So no radicals. The radicals will come from other methods, and we'll see those in a while. So the possible rational zeros are plus or minus, because we're going to recognize that both positive and a negative are factors of all numbers. So what we need are P's, factors of P. So what numbers divide evenly into 6? Well, that would be 1, 2, 3, and 6. Those are the only numbers that divide evenly into 6. So 5 doesn't divide in evenly, neither does 4. All over all possible factors of Q, which is always the first coefficient, which in this case is a 2. And the only numbers that divide evenly into 2 are our factors of 2, or 1 and 2. So now what I would do is make this into a list. So this would be equal to, here's our P's, here's our Q's. So we're going to do 1 over 1, which is 1. We're going to do 1 over 2, which is a half. We're going to do 2 over 1, which is 2. We're going to do 2 over 2, which is 1. It's already listed, so I don't need to list it again. 3 over 1, which is 3. 3 over 2, which is 3 halves. 6 over 1, which is 6. And finally, 6 over 2, which is 3, which is listed. So if this thing is going to cross the axis at a rational number, so again, fractions, repeating or terminating decimals, or integer values, then those integer values are either positive 1, negative 1, positive 1 or negative 1 half, positive 2 or negative 2, positive 3 or negative 3, positive 3 halves or negative 3 halves, positive or negative 6. So those are the only possibilities. What this does is this gives us a list of numbers to try, which is really, really important. Okay, that's all the theorems. There were 4 of them. Now we're going to pull them all together and actually find the real zeros. So on the next page of the handout, you're going to see a list of steps. These steps will help guide you through the use of the theorems to find the real zeros. So step 1, use the degree of the polynomial to determine the maximum number of real zeros. Use the rational zero theorem to identify those rational numbers that could potentially be zeros. Step 3, graph the function on your graphing utility to determine which numbers in your list are actual real zeros. Then use synthetic division to test your numbers. Each time that you have a 0 and thus a factor, you're going to go ahead and repeat the process on a depressed equation until you get it down to a quadratic, because once you hit a quadratic, you know how to solve that quadratic. And step 5, don't forget to use, if possible, the factoring techniques that you already know. Okay, that's a lot of steps. Let's combine them all together and see if we can find all of the real zeros. So this is example 5. And we're going to come back and do the one that we started the whole lecture with, which is this guy. So here's our polynomial function. F of x is x cubed plus 8x squared plus 11x minus 20. And the directions ask us to find the real zeros and then use the zeros to factor f over the real numbers. Okie dokie. So walking through the steps. The first step, I'm just going to number them over here so we have them. So step 1 is the number of real zeros, maximum number of real zeros. Well, this is a 3rd degree polynomial, so it will have at most 3 real zeros. It can't have more than that. Step 2, we're going to do our list of p over q. So this is the list of possibles. So for us, all factors of 20 would be 1, 2, 4, 5, 10, and 20. Those are the only numbers that divide evenly into 20. And so I don't just randomly start listing them. I try to make sure they're in numerical order. And then I just walk up my numbers that way I don't skip any. And this would be all over possible factors of q. Well, in this case, q is just a 1. So that 1 doesn't really impact our list. So our list really is the 1, 2, 4, 5, 10, and 20. And either positive or negative. Okay, step 3 is where we're going to make use of technology. So before technology, before we had those graphing calculators, we literally would come in and use synthetic division and try each of these numbers until we found one that had a remainder of 0. So you had to be careful, you had to slow down, make sure you didn't make sign mistakes. But we now have a graphing calculator. So we're going to come in and graph the calculator. We're going to graph that function on the calculator. So from the calculator, and again, if you don't have the calculator, you can download the Desmos app in order to be able to graph these functions. The Desmos app works well too. Okay, then what? Well, so from the graphing calculator, we're going to see that the graph crosses, that the x intercepts. It crosses the axis 3 times. We're just going to pick the one on the left. It doesn't really matter which one I pick up. I'm going to pick the one on the left because that's just the way I usually process things. So we're going to, one of the x intercepts is x equals a -5. So we're going to try -5. I could have used any one of them. I'm just picking the one on the left because it's just easiest as a class to do that. Okay, so we're going to come in and use the -5 over here, and then we'll pick up our coefficients. So I have the 1, the 8, the 11, and the -20. And we're going to use synthetic division. So notice that I'm not changing the sign on that -5. That's because as a factor, it would come from x plus 5. I don't need to change this sign when I'm writing it as an intercept, only when I write it as a factor. So we're going to try the -5, bring the 1 straight down. -5 times 1 is -5. Adding that column gives me 3. -5 times 3 is a -15. Adding that column is a -4. And -4 times -5 is a +20, which adding that column gives me 0, which we know. So we've just proved that this is indeed a factor and a 0, which we knew from the graph, but you have to have the proof, and this is our proof. The graph is not proof. Okay, but what's left down here? Well, what's left down here is an x squared plus 3x minus 4. This is the depressed equation again, just to use the terminology in the book. Depressed equation. Well, our depressed equation is a quadratic, and we know how to solve quadratic. So we're going to come in and take x squared plus 3x minus 4 and set it equal to 0. So that's going to give me x plus 4 and x minus 1 equal to 0. So x is equal to a -4 and x is equal to 1, which are the other 2 x-intercepts from that picture. So again, we could have used any of them. To answer the question, though, I'm running out of room, so I guess I'll do it here. So to answer the question, so the real zeros are the -5, the -4, and the +1. The factored form of the polynomial would be x plus 5, x plus 4, and x minus 1. So we set out to do exactly what we were aiming to do, which was to solve or find the real zeros of that polynomial function without our traditional factoring techniques. So we now have new techniques to help us factor. And then I'm going to go ahead and squeeze example 6 in because it's the same exact polynomial one more time. So just to make sure you're aware of the wording on the problems, right? So example 6 says, solve the equation x cubed plus 8x squared plus 11x minus 20 is equal to 0. I want to solve that equation. Well, wait, that's the same polynomial function. We just set it equal to 0. Well, that means we're finding, yes, indeed, the solutions, which are the x-intercepts, which are the real zeros. So when they ask me to solve, it's the same process. So we don't need to go through it again because we've already done it. But then we know that then we would get x equal to a -5, x equal to a -4, and x equal to a +1. So my solutions to this would be -5, -4, and +1. So whether they ask me to solve it or ask me to find the real zeros, the actual process is the same.